this is particle A and this is particle B, and both are approaching each other, and after interaction they give rise to new particle, particle 1 and particle 2. Say PA will be its momentum, incoming particle, and PB will be the momentum of the second incoming particle, and its momentum will be P1 and P2. It is the second particle and its momentum will be P2, right? So this is a two-body scattering process which I am considering. Now let's consider general Lorentz invariant phase space expression. Now consider general Lorentz invariant phase space expression, which we have derived in the earlier lecture. So according to this expression, that Rn, this Rne, which is a phase space expression, it can be represented as integral product of I varies from 1 to n I minus p, where I varies from 1 to n, into delta E, sorry, it is summation ei minus e, where I varies from 1 to n. So this is the expression. Now for two body, let us write down it for the two body. For two body we can write down it as, it can be expressed as that R2E, it is equal to summation, sorry, integral, and it is dqp1 over 2e1 dqp2 2e2 delta q p1 plus p2 minus p delta ei, sorry, not ei but e1 plus e2 minus e, right? So we have to write down it in this way. So let us call this as equation number 1 and it as equation number 2, right? So now let us integrate it over P2, integrate it over P2, and when I integrate it I can write down it as like this: R2E is equal to integral of dqp1, let us put these two together, so 4e1 e2 and delta e1 plus e2 minus e, let us put it like this, and d square p2 into delta q p1 plus p2 minus p. And if I recall earlier results, this integral is always equal to 1, this part. So therefore this equation can be written like this, that R2, it is simply definition of the delta function which I am considering. So R2E can be written as dqp1 4e1 e2 delta e1 plus e2 minus e, and it's integral, right? So let us do one thing. It's like a volume of the small element. So that means to take care of this, let us recall volume element in spherical polar coordinates. In spherical polar coordinates. So if I consider spherical polar coordinates, then small element dv, it can be written as r square dr sine theta d theta and d phi. So keeping this formula in mind, we can write down expression for dqp1, and dqp1 can be written as p1 square dp1 sine theta 1 d theta 1 and d phi 1. But here theta varies from 0 to pi and phi varies from 0 to 2 pi. So if I keep on doing this and do little algebra, then this can be written as, because for the closed surface dp1, this can be written like this: sine theta 1 d theta 1 and d phi 1, but its integral will comes out to be equal to 4 pi. So therefore I can write down it as 4 pi p1 square dp1. So if I put it here, then this can be written as this formula, that means R2E. It can be written as, it is dqp1 whole upon 4e1 e2. It is delta e1 plus e2 minus e, means this is the expression, and this modifies to 4 pi. This 4 pi, it can be taken outside, and dqp1 is multiplied with this, so it is p1 square dp1 over 4e1 e2 into delta e1 plus e2 minus e. It can be written like this, and its integral, so this 4 will cancel out with it. So what it will be? It is p1 square dp1 upon e1 e2, right? And pi can be taken outside and its integral, so delta e1 plus e2 minus e, right? So let us do one thing now again. What was that? Since we know that this e square is equal to m square plus p square, so keeping this in mind, I can rewrite down this as, so this can be written as pi p1 square dp1 e1 e2 its integral, and delta m1 plus m2, sorry, m1 plus p1 square under the root, this is the value of e1, keeping this in mind, plus m2 plus p2 whole under the root minus e. I can write down it in this way, right? But sorry, it's square also, it's square also, it's square also. But as we know that this p1 is equal to minus p2, this is equal and opposite. If I put it here, then this p2 square can be written as p1 square. So keeping this thing in mind, this can be written as pi integral p1 square dp1 e1 e2 delta m1 plus p1 square, m1 square plus p1 square under the root plus m2 square. It will become p1 square now, right? You have to keep in mind, because this happens in the center of mass frame, minus e, right? So that's it. So how to evaluate this? This is a very tricky thing. So how to evaluate this? Let us have a look at it, that how this thing can be evaluated. So for this, let us recall a formula. What was that formula? Recall that delta fx, it can be written as summation I 1 over f prime x into delta xi minus x. This is the formula, but here I is equal to 1. So for this, delta fx can be written as summation will not be there because one term is there, so 1 over f prime x, so delta x1 minus x. This is the formula which we are getting. So here this part is a function of momentum, right? So this is a function of momentum. So therefore f of p1 can be written as like this: m1 plus p1 square under the root plus m2 square plus p1 square under the root minus e. Now what is f prime p1? So if I take its derivative, because it also include p1 and it also include, but it is independent of p, so its derivative will be 0. And what about its derivative? Its derivative will be equal to twice of p1 over 2 m1 square plus p1 square under the root. Similarly, its derivative will be p1, twice of p1 divided by m2 square plus p1 square, 2 multiplied with it, and its derivative will be 0. But it is e1 and it is also e2, so therefore, and this 2 will cancel out with it. So f prime p1 can be written as p1 over e1 plus p2 over e2, right? So therefore delta m1 plus p1 square under the root plus m2 square plus p1 square under the root minus e, this can be written as delta e1 plus e2 minus e, and it must be written as, using this formula, its derivative will be this one. So 1 upon p1 over e1 plus p2 over e2 delta of p1 minus p. That's what we can write down it like this. So if I put its value in this equation, then this equation will become this R2E, not it is R, but it is R2 because it's for the two particle. I missed in earlier. So it is R2E. It can be written as pi integral p1 square e1 e2, it is dp1, and it is 1 upon p1 over e1 plus p1 over e2, sorry, it is p1, yeah, it is p1. So p1 over e2 delta p1 minus p. So let us do little algebra and we will get the result. So let me do little algebra, and this will be equal to, it is pi integral dp1 p1 square over e1 e2, and this part modifies to e1 e2 over p1 into e1 plus e2 into delta p1 minus p. So this will cancel out with it, this will cancel out with this. So therefore this will be equal to pi dp1 p1 over e1 plus e2 delta p1 minus p and whole integral. But as we know that f of x minus a delta, its integral is equal to f of a. So using this formula, this integral can be written as, means R2e is equal to pi p1 over e1 plus e2, and e1 plus e2 is equal to e. So therefore it is pi p1 over e. So this is the required formula for the phase space. And this p1 is equal to e square minus m2 minus m1 whole square under the root and e square minus m2 plus m1 whole square and whole under the root divided by 2e. It is the value of p1. If I put this value here, then R2e can be written as, sorry, it's like this. So it is pi over e into its value. So it is e square minus m2 minus m1 whole square under the root, whole under the root, then e square minus m2 plus m1 its square and whole under the root divided by twice of e. So this is the formula, right? So this is the required formula or the required expression. It's better to write down expression for two body Lorentz invariant phase space. Now the question arises, how do we prove that p1 is equal to this one? So let us try to prove it. This is the additional thing. You can use this result directly, but let me tell you that how this result will comes out to be there. So let us try to prove that p1 is equal to e square minus m2 minus m1 whole square under the root e square minus m2 plus m1 whole square under the root whole upon 2e. Let us try to prove it. So for this, let us consider e is equal to e1 plus e2, and this can be written as m1 plus p1 their square and into square root plus m2 square plus p2 square under the root. So from here I can write down that e minus m1 square plus p1 square whole under the root is equal to m2 square plus p2 square under the root. So squaring both sides, so if I take square on both sides, means how I can write down, it is e minus m1 square plus p1 square under the root whole square is equal to m2 square p2 square. Sorry, it's not p2, it's p1. Let me check it. Yeah, it is p1, as I have talked about it earlier. So it is p1 under the root whole square. So this square and square root will cancel out, and applying here formula of a plus b whole square. So it is e square plus m1 square plus p1 square minus twice of e m1 square plus p1 square under the root is equal to m2 square plus p1 square, and this p1 and p1 square both will cancel out on both sides. So now this e square plus m1 square, put it here, bring this towards this side, plus m2 square is equal to bringing this towards that side, so it is twice of e m1 square plus p1 square under the root. Now again taking square on both sides. So if I take square on both sides, then this part can be written as like this, that e square plus m1 square plus m2 square. It's not m2, so it's not plus, but it is minus. It's minus because I bring it towards this side, it will become negative, right? So here again, let me correct it. Minus m2 square whole square is equal to it is 4e square m1 square plus p1 square, because our purpose from here to evaluate the value of p1. That's what I am doing here, little algebra. So it is e4 plus e4 plus e square m1 square minus e square m2 square, then plus m1 square e square plus m1 raised to power 4 minus m1 square m2 square, then minus m2 square e square m2 square e square minus m2 square m1 square or m1 square m2 square, m1 square m2 square, and it is plus m2 raised to power 4 is equal to 4e square m1 square plus p1 square, right? So let us do little algebra. E raised to power 4 will remain as it is, so it is e square m1 square, and both are similar, so it is twice of e square m1 square. And let us have a look at this part, means this, and m2 e2, it will be somewhere here, m2 e2, yeah, right, m2 e square, right? So it is, both are negative, so it can be written as minus e square, sorry, yeah, it is minus e square m2 square. And similarly another is this one, both are negative, so they can also put together, so it is minus 2 m1 square m2 square, right? And if I solve this, then it is 4e square m1 square minus plus 4e square p1 square. So bringing this towards this side, it is minus 4e square m1 square, and another two terms are more. One is this one, it is m2 raised to power 4, and m1 raised to power 4 is also there. So let us put m1 raised to power 4 plus m2 raised to power 4 is equal to 4e square p1 square. So now let us put these two terms together and put these along with this. So I can write down this term as, this is e4 plus m14 plus m2 raised to power 4 and minus 2e m1 square minus 2m1 square m2 square 2e m2 square is equal to p1 square and whole divided by this 4e square. Right, that's what we are getting here. But this can be written as like this. Let us have a look at now this term. So this e4 minus m14, sorry, plus m14 plus m2 raised to power 4 minus 2e m1 square minus 2 m1 square m2 square minus 2 e m2 square, it can be written like this, that it is lambda e square comma m1 square comma m2 square. This is like a Mandelstam variable, and for this let us recall and this can be written like this. This is equal to e square minus m1 square under the root plus m2 square under the root whole square, and similarly it is equal to e square minus m1 square under the root plus m2 square under the root, sorry, minus will be there, and its whole square, right? This is like Mandelstam variable. Sorry, it's not Mandelstam variable, but it is a, let me do, it's not a Mandelstam variable, but it is a it's not a Mandelstam, but what do we call it as? I'm not remembering. Let me remind it. It is Callan function. This is like a Callan function, not Mandelstam, but it's like a Callan function. Right, so using this I can write down this is equal to this one. So for this let me remind a formula, means what was the formula for the Callan function? That is lambda x y z. It can be written as x square plus y square plus z square minus 2xy minus 2yz minus 2zx, and this can also be written like this: x minus under root y plus under root z whole square, and x minus under root y minus under root z its square, right? So this is a Callan function. So basically I use this formula here, and keeping this in mind, let me remodify it little bit. So if I modify it, then it can be written like this. It is e square, it is m1, because this square will cancel out with this will happen here. So it is e square m1 plus m2 whole square, sorry, yeah, it was like this, and it is e square minus m1 minus m2 its whole square. So but m2 plus m1 square is also similar to m1 plus m2 square. Similarly, m2 minus m1 square is also equal to m1 minus m2 square. So keeping this in mind, I can rewrite down it as like this: m2 plus m1 whole square and here it is e square minus m2 minus m1 whole square. So it can be written like this. So therefore p1 square, this p1 square, it can be written like this, means it is e square plus m2 minus m2 plus m1 into e square minus m2 minus m1, this divided by 4e square. So taking positive value, so p1 can be estimated like this. So it is e square minus m2 plus m1 whole square and e square minus m2 minus m1 whole square under the root twice of e. So this is the value which we have used to get the phase space, right? So this is the results. So that's all for this lecture.